Welcome everybody to the SCENIC tutorial at CVPR 2024. My name is Sanjit Seshia. I'm a professor at UC Berkeley. And I'll be presenting today together with Daniel Fremont from UC Santa Cruz and Edward Kim, also from UC Berkeley. The SCENIC project is something we started at Berkeley over 6 years ago now, in 2017, 2018. SCENIC is an open source probabilistic programming language and an associated system for AI safety in general, particularly in the context of autonomous and semi-autonomous systems, but also for data generation. And SCENIC has evolved over the last 6 years, and we've had many users and contributors. And at the outset, before we dive into the tutorial, I want to express our thanks to our many SCENIC team members over the years and the many contributors around the world. And they're all listed at that website over there. There's a lot of information at our webpage, sceniclang.org. And also I want to point out that we have this website, sceniclang.org/cvpr24, which has the slides in PDF that we'll be using today. So if you'd like to consult that as a handout during the tutorial, you're welcome to go to that website. It also has the Google Colab scripts that we'll be using in the hands-on section of the tutorial in about an hour. Okay. All right. So I want to start by setting some context here for the next 25 to 30 minutes for why we created SCENIC and what sort of use cases it enables. Okay. So the context for the SCENIC project 7 odd years ago was that we, even at that time, saw that there was already a proliferation of machine learning and more broadly of AI in all kinds of autonomous and semi-autonomous systems, particularly those that are safety critical and operate in a cyber-physical context where computation is tightly integrated with the physical world. So autonomous vehicles, self-driving cars are a very popular and widely described example of this, but it is much broader than that. And you'll see many more examples in this tutorial. And so over the last many years, we've only seen this, this use of machine learning and AI in these contexts grow. And at the same time, I think we're all well aware that a major obstacle to the broader adoption of this class of systems has been a general lack of safety, dependability, and robustness. So those of us who were around and looking at following the news about 10, 15 years ago will remember the rosy predictions that self-driving cars will be widespread and on the roads by 2020. Well, 2020 came and went, and realism set in, pessimism set in. And I think people realize that this is a much harder problem than they originally thought or marketed to be. And unfortunately, there have been several accidents, incidents. I think many of you would be familiar with these cases that have actually shown us that these sorts of machine learning driven systems have to be designed with utmost care, especially when they operate in these sorts of safety critical settings. So that's really the context where we started this work. It's part of a broader agenda we call the Verified AI Agenda. So SCENIC is, I think, a centerpiece of this, but the overall agenda is to really create a design flow. And what I mean by that is to essentially create a set of algorithms and underlying theory and software tools that will support the design of these systems across the entire life cycle. Okay, and ultimately we want to use these to ensure safety, dependability, and robustness. And some of us wrote an article setting out our thoughts on this many years ago, and there's a revised version in the Communications of ACM in case you're interested in taking a look. I won't touch upon the details of that very much here. Several of us come from the field of formal methods within computer science and engineering. We see this field as a key enabler for AI safety. And it's one that I think has to work together with all the other fields, including computer vision and robotics and AI in general. So what does formal methods bring? So one thing we hope you'll take away from today's tutorial is that it provides you a notation for precise and programmatic modeling of the world, which is these AI systems and their environments, which can be very complex, right? So SCENIC is actually a step towards trying to capture these world models. It also gives you a mathematical notation to specify requirements and metrics for these systems, um, scalable algorithms for verification, synthesis, testing, and debugging, and also an overall design methodology for probably robust design. And the work I'm describing today has been supported by many agencies over the last several years. Notably, right now, we are supported by a National Science Foundation open source ecosystem project. Okay, so there are two open source tools that have come out of this, and that's really the focus of this tutorial today. SCENIC is a high-level probabilistic programming language for world modeling. Verify is the supporting backend toolkit for requirement specification and algorithms for the various steps in the design cycle. Okay, and these have been open source for many years now. We have a growing user community, and we hope many of you will also join that. These are tools that are being used in industry, in academia, and also we're working with people in government and regulation agency. And of course, there are different use cases across all of these sectors. What we'd like to do, and this tutorial is part of that, is to grow this open source community because we think it's really an open approach to AI safety that will sort of have the greatest impact. Okay? Yes, question. Yes, I said that at the beginning. It's just go to the website, sceniclang.org, CVPR24, and you'll find the slides there. Thank you. Okay, great. So with that overall outline of today's tutorial, it's a little bit less than 3 hours from now. I'll continue and I'll do an overview of SCENIC. And what I'd like to do is just give you 2 examples of industrial case studies that we did with SCENIC and Verify. And that hopefully will give you an idea of what it can do. Then we'll get into the how. So Daniel will then give you an introduction, an in-depth introduction to the SCENIC 3.0 language. And this will be a hands-on section of the tutorial where you'll get your chance to write SCENIC code. That takes us into the coffee break. After the coffee break, we'll talk about applications of SCENIC, a few exemplar applications. So Edward Kim will come in then. We'll talk about how you can systematically test and debug various components in the autonomy pipeline, including perception, prediction, planning, or even the entire autonomy stack in simulation. We'll also show you how you can generate sensor data, how you can do logging and generate labels using SCENIC, and also do sim-to-real validation. And then finally, we'll conclude with some ongoing and future directions. We have some exciting applications in augmented and virtual reality, and Eddie will tell you a little bit about that. We'll talk a little bit about SCENIC and large language models and a few other things. Okay, and of course, feel free to ask questions during the tutorial, and we'll be happy to do that online as well as after each segment. Okay, great. So like I said before, SCENIC is a language for environment modeling and data generation. It's a probabilistic programming language. What that means is that in a SCENIC program, every program variable is a random variable. The distributions are defined by the syntax of the program. Some distributions are implicit. They come from library definitions and things like that. Some are explicit. We'll call a scene as a static snapshot of the world at a point in time. A scenario is a dynamic evolution of the world over a sequence of time steps. Okay. So there's many use cases of SCENIC, and of course, this tutorial is all about that. But I wanted to give you an example of what SCENIC looks like. So when we designed SCENIC, we designed it to be hopefully readable and easy even for non-programmers to understand. So it's kind of a mix between Python and English. So this is a simple SCENIC program, which is an example of a scene, a static snapshot of a badly parked car at a point in time. Okay, and so I think Daniel will go through this line by line. But broadly speaking, we define an ego object from whose viewpoint the world is being perceived. And then from the viewpoint of the ego object, we pick a spot, we pick an orientation, which is a bad angle, and we place a card there. And then when we connect this to a backend renderer or simulator, in this case, the renderer of the Grand Theft Auto 5 game, every time you run the SCENIC program, it randomly generates a new configuration, and then you render that configuration, and that's the image that's being displayed. So that's static version of SCENIC. So you can also define dynamics in SCENIC. So this is the same badly parked car example. And so as you can see here, this part down here looks almost the same, except that now both the ego object and the badly parked car have behaviors, right? So the ego behavior is this one, which is not defined here on this slide, but it's basically lane keeping and emergency braking. And the badly parked car's behavior is defined up here. So what this does is it waits until the distance between itself and the ego is less than 15 meters. And when it is less than 15 meters, it pulls into the path of the ego vehicle, right? So kind of a slightly adversarial behavior. And now you can, each time you run this and you connect it to some backend, in this case, the Carla self-driving simulator, you see that as the car approaches, the badly parked car will pull into its path. Okay, and once again, what's happening in the backend is that SCENIC, the SCENIC programming system, it has a sampler that is sampling from the distribution underlying the SCENIC program. And obviously, one thing you'd like to do is have the samples be sort of maximally diverse to give you a diversity of actual simulation. Okay, so SCENIC was first created back in 2018, and over the years, we and our collaborators have demonstrated various applications. We started out looking at data generation as well as modeling, testing, and verification, as well as exploring the performance of an AI system in different environments. This one is a toy Mars rover example. We also applied it in the context of computer vision, object detection, to debugging machine learning neural network-based perception. So this is a case where a neural network at the time state-of-the-art for object detection thought that there were 3 cars, but there was just one. And we were able to use SCENIC and a form of debugging that's known as delta debugging in software engineering to try to understand what the root cause of this failure was. So you can, of course, use SCENIC to generate synthetic data. You can also use it to do design space exploration. And as I mentioned, there's a backend to SCENIC, which is the Verify toolkit. The Verify toolkit, if you focus on here on the right, it supports a variety of use cases across verification, debugging, and synthesis. So we can do things like fuzz testing. Falsification is like goal-directed failure finding. Statistical model checking is a approach where you can provide a statistical guarantee on the probability that a safety condition holds. And then you can also support a variety of other use cases. One of the features of Verify is that it has this internal representation we call the semantic feature space over which all the algorithms can operate. And it can have been applied to a variety of domains. So speaking of application domains, this slide shows 5 of the domains that have been explored. So autonomous vehicles is a popular one that we started with, but we've also applied it in collaboration with people at Boeing to aerospace systems, in collaboration with people at Toyota and other places to indoor robotics, to multi-agent systems like the soccer playing example that you see here, as well as to augmented reality and virtual reality applications. Okay. All right, great. So that was a bit of a quick intro to what SCENIC and Verify are, and you'll see the details soon. But what I want to do is give you 2 industrial case studies of what we did along with our collaborators, one in the avionics domain and one in the autonomous driving domain. Just to give you an example of what I mean by a design flow, right? So SCENIC is a representation. That representation is kind of the centerpiece of the design flow. All the steps in the design flow operate on the representation in different ways, and they use the representation in different ways. Okay, so this particular example was one that was posed by Boeing in the context of a DARPA program called the Assured Autonomy Program. And in this particular case, Boeing posed a challenge problem to all the participants, which was a problem of autonomous taxiing. So they created a neural network they call TaxiNet, and then they created an aircraft steering system around it. So an experimental autonomous aircraft taxiing system, where you see here on the right a little image of the nose of the plane. And so the plane has 2 wings, left wing and right wing. And there's a camera mounted on the right wing of the plane. And the image comes from that camera. And this image is fed into a neural network. And the task of the neural network is to estimate what's called the cross-track error CTE, which is the deviation of the nose of the plane from the center line on the runway. And so that estimate then goes into a conventional controller, which will control the steering and the throttle of the plane on the runway. Okay, and so the overall objective of this particular system was to keep the plane within 1.5 meters of the center line, so plus or minus 1.5 meters of that center line. Okay, and here's an example of the taxinet system doing a reasonable job. So you can see here, it's keeping the nose of the plane on the center line in spite of these skid marks that you see on the runway, which are obscuring the center line at many places. Okay, I must say all of this work was done in the context of a simulator. So this simulator is called X-Plane. It's one that folks in the avionics domain have used for many years. Okay, so so here's what we did with our tool SCENIC and Verify. Step one, we modeled the runway scenarios in SCENIC after talking to our collaborators at Boeing. Again, note Boeing just gave us the neural network, but no other information about what it was trained on, or what sort of particular training scenarios were used. What they did tell us, though, is that this is the expected type of environment it's going to work in. Okay? And that's what the SCENIC program models, which I'll show you in a bit. Then they also told us what the safety requirement is, which is to keep the plane within 1.5 meters of the runway, of the center line. Then we ran our tools. So the Verify toolkit has this technique called falsification, which you will learn about when we talk about applications. And this is an algorithmic method for finding concrete scenarios or test cases where the system violates its safety specification. Once once we find these kinds of failure scenarios, then we want to do debugging to understand why the system failed and do some root causing. And then once we understand the reason of the failure, then we can improve the system, which in this case means we retrain the neural network so as to improve its performance. And then that process of these 5 bullets can be iterated. But of course, one of the things that all designers of this class of systems must keep in mind is that even if you specify a model of the world in which it's supposed to operate, at runtime, there's a good chance that the world will not behave in that way. And so you have to be able to at least detect that and say, oh, there's a deviation from what I expected the environment to be like. And then you need some mitigating action, right? And so this is called runtime assurance. And so we've also done work on learning these kinds of monitors that will tell you whether you are in distribution, the SCENIC program, or you're out of distribution. And if you're going to go out of distribution, then it will take some mitigating action. Okay. So let me go through each of these steps. So step one is modeling with SCENIC. And let me move this box out of the way. So our collaborators at Boeing told us that the environment is pretty straightforward. The only thing that changes is the time of day, which can be anytime between 6 a.m. and 6 p.m. So that's what you see modeled in that line, Zulu time. Whether there are clouds in the sky and what kind of clouds there are, and this is something the simulator can set. Whether there's rain and how much rain there is, and the initial position and orientation of the plane on the runway. And so you see each of those things described here, time of day, clouds and rain, and then the position and orientation down there. Okay, so that's it. That was the SCENIC program, very simple at that point. Of course, SCENIC has a lot more features, as you will see soon. So given that SCENIC program, the next step is specify the safety requirement, which we write in a notation called temporal logic. If you don't know temporal logic, don't worry. I'll just tell you what this means in English. It just means that sometime in the first 10 seconds, the plane gets within 1.5 meters of the center line, and it stays there forever. Okay, and so what falsification does is it takes that logic property and it turns it into a cost function, and the cost function is then minimized. Okay, and if you're able to drive the value of the cost function below 0, that corresponds to a violation of safety. That corresponds to an unsafe execution. Okay, and so when we ran our falsification algorithms in the Verify toolkit, it automatically generated about 4,000 simulations, and 45% of those violated the safety property. Okay, so a large chunk of those simulations were unsafe, and about 9% left the runway entirely. And here's an example of one of those unsafe cases. Early morning, low light, light rain, and you can see the neural network has lost the center line and is proceeding to drive the plane off the runway. Okay, so this is completely automatically found based on the SCENIC model and the Verify algorithms. Okay, so there were a lot of these, of course, right? Like literally a few thousand of them. And so the next step is to understand what went wrong. And so we tried to, based on our SCENIC program, analyze which features of the SCENIC program are more highly correlated with failures. Okay, and in particular, what we found was that performance was particularly sensitive to time of day. So what you're seeing here is a graph where the x-axis is the time of day going from 6 a.m. to 6 p.m. And the y-axis is what is called the robust satisfaction value, which is the value of that cost function I showed you. So negative means unsafe, positive means safe, right? So anything above the dashed line is safe, anything below the dashed line is unsafe. And so you see here, early morning tends to be unsafe, and then it tends to be safe in late morning, and then again, and early afternoon, but again here, sort of mid-afternoon, it becomes unsafe, and then again in the evening. Okay, and so we wanted to understand what was going on there. Early morning, you saw an example of what might be going on, right? Low light, and it's not able to do so well. The afternoon, though, was a bit of a puzzle to us until we used SCENIC to generate simulations that correspond to what was going on at that time. And you see the shadowing effects kick in the mid-afternoon, right? And this is particularly when it's like a cloudless sky and you can get a good shadow of the wing. Okay, so there's this combination of time of day plus cloud cover and so on that leads to failures. Okay, so now that you understand the failures, what we can do is we can again use SCENIC to produce new data, but this data will be generated in a programmatic fashion to be able to augment the data set exactly in these cases where you see those failures, right? And when we actually went back to Boeing and asked them, what sort of data did you train it on? Was it, was it not early morning, low light, etc.? The answer was yes. They actually trained it with very basic nominal conditions midday. Okay, so using SCENIC again, we were able to generate data and retrain it, and overall, we obtained much better performance on the retrained neural network. So here's a particular environment configuration, exactly the same in the top and bottom. The original neural network, as you can see, is proceeding to drive the plane off the runway, and the retrained neural network is doing a much better job. Okay. All right, and then you see that quantitatively also. So the blue line now is the performance of the retrained, which the median value is always above 0. Okay. Finally, I talked a little bit about runtime monitoring. Maybe if you can hold your question, let me cover this and then I will take your question. Okay. And so there's an obvious question of, okay, well, that was all with respect to that SCENIC program, that particular model of the world. What happens if there is something different? Okay. And so for this, we learned a runtime monitor which corresponds to the support of that SCENIC program. And it's predictive, so it can tell you whether you're in distribution or not with some look ahead. So now you can see it says trusted environment in the corner. It's running a system that's called Simplex, which is a very classic approach in fault-tolerant computing, where you have a monitor, which is the thing in the black box up there, and it's continually monitoring certain inputs that we trust, like the position of the plane and maybe the weather report at that point in time and so on, but not the neural network's output here. And you can see here that actually it was maybe a little discernible, hard to discern, but it says here untrusted environment. And at that point, actually, the plane was starting to drift a little bit to the right. And then the system says untrusted, it flips over to a more trusted controller. Okay. All right. Yeah, there was a question there?
Yes. First question is, how does it capture all of the real-world physics from everybody? And my second question was, how do you know which factors to model that potentially affect cost function. So like one was time, but there could also be weather, some other sort of external factor that we might not even think of or know of.
Yes.
So how do you encapsulate that whole?
Yeah, great questions. So for the first question, the physics, you can think of the SCENIC program as a high-level model, which doesn't actually model the sort of the detailed. It doesn't give you a detailed physical model of the how the plane works or so forth. Those are delegated to a backend modeling system, which could be part of your simulator. Okay. So think of SCENIC as sort of a high-level modeling language. You could get fairly detailed in SCENIC if you wanted to, but for all of these cases, we kept it as a high-level model. For your second question, what happens if there are features or factors that are not in your SCENIC program, right? I would give two answers to this and maybe revisit this at the end of the tutorial, right? This relates to how do you generate the SCENIC program as well, right? And so, depending on if you're doing it manually or if you're trying to have some automation there, you can, if you're doing something automatically, you can try to generate this in a way that captures all the different features that are present in actual data that you might have generated or may have collected previously. But this is a model, right? All models are wrong in some ways. And so there's always going to be things that you missed. And so we need other mechanisms. And that's exactly what the runtime monitor was doing. The runtime monitor is basically saying, I'm just going to tell you based on a trusted subset of the variables in my SCENIC program, whether you're in distribution, out of distribution. It might be conservative, right? It might give you false alarms in that regard, but it'll at least tell you whether you're likely to be stepping out of the distribution of the SCENIC program. And if you are, then you have to have some other fallback. Okay. Yes. Yeah. Right. Why don't we defer that question until after Daniel finishes, so you'll understand the language better. Yeah. One more question. Yeah. Yes. Different model. Yeah. The backend model, easy or? Yes, and that's also a question that will be addressed a little later in the tutorial. Like, how do you interface to different simulators? We'll definitely address that. Okay, I know I'm running a little behind schedule, but I really want to cover this, but I'll be quick. And then in about 5 minutes, I'll switch over to Daniel's section. Okay, so we saw an example of a case study of using SCENIC with a simulator, right, for that avionics application. Another industrial case study we did in the context of autonomous driving was to see if we can go from simulation to real-world testing. That is, answer two questions, really. One is, if we use SCENIC and verify in simulation in this way, and we find these failure scenarios, how well do they transfer to the real world? And secondly, can we actually use what we're doing in simulation to design experiments for real-world testing, right? Because real-world testing is expensive, it's tedious, it takes a lot of time, and so you want to be very careful about how you design those experiments. And so this is a work that we did a couple of years ago in collaboration with LG. At the time, they were creating a autonomous driving simulator, and also the American Automobile Association, AAA, that runs a big test facility in the San Francisco Bay Area called Gomentum. And the particular approach is shown on the slide. So step one is create the simulated world, which is the area of Gomentum that we were doing the tests in. Specify a particular scenario in SCENIC, specify safety properties, then run our falsification algorithms and verify. And then just in the Boeing case study, we'll get simulations that are both safe and unsafe. Now what we want to do is, based on this, we want to select a small set of test cases that we'll actually run on the road at Gomentum. And so we selected those, we actually executed those on the track, and then collected data and analyzed. Okay? And all of this is reported in that ITSC 2020 paper listed below. But I'll just give you like a 3 or 4 slide overview of this. So the particular scenario we looked at was a autonomous vehicle pedestrian crossing scenario, in particular because the for especially for autonomous vehicles, but also in general for all kinds of traffic. Unfortunately, pedestrian and what are called vulnerable road users like bicyclists and so on, the number of incidents and accidents has been growing, and it's always been it's a huge um, segment of scenarios that we have to be careful about with autonomy. So the specific scenario is the one that's shown here in the map on the right. So there's an autonomous vehicle which you see up here. It has a LiDAR on the top. This was a few years ago, so it was running an old version of Baidu's Apollo software. The AV starts down here on First Street, and it follows this blue dotted path. And the goal of the AV is to end up here on Pearl Street at the endpoint on the top right. But along the way, when it turns from First Street to Pearl Street, there's a pedestrian crosswalk. And this is created using the typical crash dummy apparatus they have, where there's a track where the pedestrian dummy starts here on the yellow dot, and it's going to cross over to the red dot. But the particular scenario we modeled was one where the pedestrian hesitates in the middle. Okay. And the SCENIC program is much bigger, but I'm just showing a couple of relevant lines there. And so we can model the ego vehicle with a behavior which is simply to follow a path and drive through the endpoint. And we model a pedestrian behavior, which has three key parameters. The first is the time between which the AV starts and the pedestrian starts, which is a uniformly random number selected uniformly at random between 7 and 15 seconds. The distance the pedestrian dummy travels before it hesitates, which is between 4 and 7 meters. And then the time it hesitates, which is between 1 and 3 seconds. Okay, and once again, as just in the case of the Boeing case study, our falsifier generated lots of simulations. 2% of those violate the safety property, which is that the car got too close to the pedestrian dummy, didn't necessarily hit it, but it was close enough that it was unsafe. And this is a visualization of all of those simulations where a warm color means that it's safer, and a cold color like purple or blue means it's unsafe. And then what we did was to select test cases to execute on the track that were either robustly safe, which is it's like a safe simulation and its neighborhood, even if you perturb those random variables, will also stay safe, at least in the simulations we explored. Something that's marginally safe, which is it is satisfying the safety property, but if you perturb the random variables a little bit, it can flip to unsafe. And then those that are unsafe with an unsafe neighborhood. Okay. And what we found was that in our experiments, if something was unsafe in simulation, then majority of the time it was also unsafe on the road. And we found some collisions as well. And if it was safe in simulation, it was safe on the road. And the paper actually goes into a lot more detail of what was going on. But here's an example of an unsafe scenario that was found in simulation and also replicated here on the road. So you see the car is coming up here on the bend, and it actually detects the pedestrian dummy. So the dummy is hesitating, but then it drives into it anyway, right? And so that's an example of something that we found in simulation we're able to replicate on the actual road. And then when we replayed this within Apollo's visualizer, it was clearly at one level a failure of perception. So you can see here the autonomous vehicle starts to go down First Street on the turn, and you can see the fence over there, which is where it wants to go. And now you'll see the pedestrian appear. So that's the yellow box. So the car sees the pedestrian, it puts a fence, it knows it has to stop. And then at some point it loses the pedestrian turn, right? And so it seems like initially there was a failure of perception. Well, of course, you want to design the stack to be robust. So there should have been some prediction there, and I don't know what happened there. And there should have been some human intervention, and that also did not happen. So anyway, in all of these things, of course, there can be multiple levels of failure. But the point is, using these tools, you can actually, we were able to do fairly efficient transfer of sim to real. Okay, so we have now an ecosystem of design tools around these open source tools, SCENIC and Verify. I won't go through all of these details here. I'll mention two other applications that Edward Kim will talk about. the multi-agent games as exemplified by the soccer example. And we can model these sorts of different player strategies and scenarios also using SCENIC. And then also model the world for virtual and augmented reality also using SCENIC. Okay, and with that, I'll move over to Daniel. And as Daniel is getting set up, I can take any more questions.
In the example, I think taking more than from your camera, does SCENIC generate more than that?
Yeah, so let me show the other side. So that particular system, AD system, had LiDAR, and it's so I don't think it's like an apples to apples comparison with what Baidu may have now. This was 4 years ago, and LiDAR was the primary sensor that was being used there, and so it's hard to tell exactly what may have happened because first of all, in simulation, the type of LiDAR that was being simulated was lower quality. So there were several failures that we found in simulation that did not happen in the real world because you had a better LiDAR. Now, in this particular case, it could have been that, it's speculation, but it could have been that because the LiDAR was in the top and the dummy was close enough that it wasn't able to catch the dummy. Yeah, but anyway, I mean, I think there's multiple, one can analyze the reasons, and the paper has a bit more details of what that might have been. SCENIC can model the world, and then the simulator will generate the LiDAR data. And Eddie Kim will go into that in more.
Okay, so the plan for the second part of the tutorial here is we'll go into more detail about how the SCENIC language actually works. We'll start, oops, here's the rough plan. We're a little bit behind schedule, so we'll probably just shorten these sections a little bit, but we'll break it into two main parts. So we'll start out by telling you how to define what you could call static scenarios in SCENIC. So just programs in SCENIC that will generate scenes, not expressing how things are changing over time. We'll start with that. So I'll give a brief overview of the language features that SCENIC provides for doing that, and then we'll have time for you all to actually try using those yourself in a Colab notebook we've put together. I'll show a QR code. It's also linked from the CVPR website that Sanjit showed earlier. So we'll do that for a while, and then a little after 10, we'll pause again. I'll show you some more features of SCENIC, this time that are useful for describing dynamic behaviors. So what's going on over time. And then we'll have a second Colab notebook where you can play around with those features. And then I'll conclude just mentioning a few more advanced features of SCENIC that we won't have time to get into in detail, but just so that you know they're out there. Then we'll have the break before Eddie will tell us about applications of SCENIC in more detail. So just to start out here, I want to give a brief history of SCENIC because we're going to be using a particular version of SCENIC, the most recent one, SCENIC 3, which we just officially released the other day. And so this is going to be accumulating features we've had in several different versions. If you go back and look at some of our papers that Sanjit cited, you may see slightly different versions of the syntax from older versions. So the first version of SCENIC from 2018 and then in our paper in 2019 was just about static scenarios. And it also had a 2D world model, which was good enough for most autonomous driving scenarios, for example. So we saw the interface to GTA 5 that Sanjit showed. We also had an interface to robotic simulator, Weebot. And most of the features we'll talk about in the first part of my section here will be from that. And then in SCENIC 2.0, which is in this extended version of our paper in the Machine Learning Journal, that allow you to talk about dynamics. So that's what we'll see in the second half. We also introduced there a driving scenario library that lets you write scenarios involving cars, pedestrians, and so forth in a simulator agnostic way. So you can write a scenario that works in, say, Carla, but also this LGSVL simulator we had, or any other driving simulator that you can write an interface to SCENIC for. And then finally, just last year, we introduced this latest version of SCENIC, which now has support for 3D scenarios. So a lot of things have changed about the internal representation of scenarios so that you can now talk about things in 3D. And in particular, we now have precise modeling of shapes and occlusions. So it's possible to reason about things like a pedestrian which is obscured by a car that's in front of it, for example. And there are a lot of other new features which we'll see that were added in here, like the ability to express requirements in temporal logic. Okay, so to start out here, let me go through in detail this badly parked car example that Sanjit showed before. So on the left-hand side here, we have a kind of schematic of what we want. So we have the ego car, which is over here, and it has some view cone, which I'm showing in blue. And somewhere over here, we have another car, which is a little bit too far away from the curb and not really parallel with it. So how are we going to model that in SCENIC? The first thing we're going to do is specify what's called a world model that we're going to use. SCENIC itself is not specific to autonomous driving. As you saw, we have plenty of other application domains. So this model that we're using here is basically a SCENIC library that defines all the concepts specific to autonomous driving. So what is a car? What is a pedestrian? What are roads? These kinds of things. And in particular, that's defining a class of object called car. And so we're saying create a new car and let that be the ego object for this scenario. So that's where the camera is going to be rendered from by default and so forth. And notice we're not saying anything about this car in terms of where it is, what color it is, and so forth. So SCENIC is using the default values for all of those properties, like the position property, the orientation property, etc., that are defined in this car class. So for example, the driving library says that the default position for a car is a uniformly random point over the entire road network, but not, for example, on the sidewalk. This is like a reasonable default value to have if it's not otherwise specified. Likewise, for orientation, the default orientation for a car is parallel to the road at whatever point it is. Okay, but for this second car, we want to say something more specific about that, namely that it's near the curb and has this different angle. So the way we're going to do that is in a few steps. The first thing we're going to do is pick a spot on the curb to place this car near. So zooming in a bit, this red line here is showing the curb, which is a region in SCENIC. So SCENIC has a data type called regions that represents a set of points in space. And this driving library defines a region called curb, which represents all the points on all the curbs in the whole road network. And we want to pick the part of the curb which is actually visible from the ego. So here was that part of the view cone. We want this part highlighted in black, the curb which can actually be seen by the ego. And then we want to pick a random point on that. So how we're doing that here is we're starting from this curb, which, as I said, is a region. That's a primitive data type in SCENIC. And we're passing that to a built-in function in SCENIC called visible, which will restrict this curb region to just the part that's visible from the ego. Then we're saying to create an oriented point. So an oriented point is a built-in class in SCENIC, which basically just represents a position and an orientation in space. So this is useful for defining like a local coordinate system without having to actually create an object. And the way we're creating this oriented point is using this on syntax. This is an instance of what's called a specifier in SCENIC. So we'll see in the tutorial, the hands-on part, there are a lot of different specifiers that SCENIC provides, which correspond to different natural language ways of specifying the position or orientation of an object. And you can mix and match these to build up a definition of an object in a convenient way. In particular, this on specifier says, take this region, the visible curb, and pick a uniformly random point in that, and then place the car on top of that. Or in this case, place the point on top of that. So the net effect is to give us a uniformly random point among the visible part of the curve. Okay, and it's oriented, so this part is not so obvious here, but actually SCENIC knows that the default orientation to use for something sampled from the curb should be parallel to the curve. And that will come out, question.
Yes, what's the significance of the italics? In the car, it's the instance is italicized, and the next one, the class is italicized.
Right, thanks. So it's the syntax highlighter shows built-in types in italics. So car is not built into SCENIC. It's something we define in this library, but oriented point is built into SCENIC.
What about the instance ego?
Right, and so ego is a variable with a special meaning in SCENIC. So it's also italicized and drawn a different color here. Right. Okay, so the next thing we're going to do is pick an angle for this car to be parked at. And the way we're going to do that is we're going to say, pick an angle uniformly at random between 10 and 20 degrees. So this is a uniform distribution over that interval. and then multiply it by either 1 or -1 with equal probability. So we'll end up 10 to 20 degrees left or right. That's the angle we want this car to be parked at. And now we can start actually creating this car. Now notice we want it to be some ways away from the curb, so maybe say 0.5 meter off. In order to place the car 0.5 meter from the curb, we need to know how wide the car is. If the car was wider, we'd have to place it further away so that the gap was still 0.5 meter. And this is something that SCENIC can figure out automatically. So here, this left of syntax, this is another one of SCENIC's specifiers that implicitly depends on the width property of the car. So SCENIC knows before I can evaluate this, I have to sample the width of this car. Then I can figure out how to get 0.5 meter to the left of that spot. And another thing that SCENIC is doing here is this spot has an orientation associated with it. So we're going 0.5 meter to the left of that spot in its local coordinate system. So it's not 0.5 meter due west, it's actually 0.5 meter into the road. That's why we use this oriented point here. Another question. Right, so here the question is, where is the width coming from for this car? So we didn't specify it. So it's the default values being used. And if I showed you the definition of the car class, the width is actually defined as being derived from the model property of the car. And the model property is a distribution over a bunch of different types of cars that the simulator supported. So here what's actually going to happen is it will pick a random type of car, like should it be the taxi or the school bus or various different types. And then from that, it will get the width, the dimensions of the car. And then that's what gets used here. Yeah, so in this driving model, we basically provide a bunch of different types of cars that the simulator support that we were using supported. And by default, there's some distribution over those types. If you had a simulator with different types of cars, you could, of course, specify that. Yeah.
Is the 0.5 probabilistic or deterministic?
This one is fixed. I just said exactly 0.5 meter, but I could have done a range, for example, if I wanted to. Okay, so this specifies the position of the car, but we haven't said anything about its orientation. So that's what I'll do next. I'm using another specifier here, the facing specifier, to say this car is facing this funny angle. Again, we don't want that to be in the global coordinate system where 0 is due north. We want it to be relative to the road direction. And here, road direction is another primitive, SCENIC object called a vector field, which is being defined in this driving model, which basically says at every point on the road, what is the nominal traffic direction at that point? And so this relative to operator is interpreting this bad angle relative to this vector field. Another interesting thing there is the vector field defines a different direction at every point in space, but SCENIC knows because we're defining this car, I should look up the position of this car. So SCENIC here will figure out, okay, first I have to compute the position using this left of, which recursively requires that we figure out the width and so forth, before we can then go on to evaluate this facing specifier. Okay, that's the whole program. There's a little bit more that will happen here in the background. SCENIC has some constraints built into it. So it knows, for example, that objects cannot intersect each other. You can disable that on a per object basis if you want, but it will ensure for us that these two cars won't actually collide, that this driving library says that by default cars have to be fully contained within the road and so forth. So if we then put this program in SCENIC, we can run the sampler and it will generate scenes, which we can import into a simulator. So here we've imported them into GTA 5, and you'll see we get a variety of different instances that meet that high-level description. We've got a car, it's near the curb, but the angle is somewhat funny, but lots of other things we get the diversity over. So the distance to the car, the weather, time of day, these sorts of things, and the type of car, etc. So that gives you an idea of some of the key concepts in SCENIC. So what we'd like to do next is give you a chance to play around with these things. So we have Google Colab Notebook, which you can find at this QR code, or if you're on our website for the tutorial, it's also linked to there. So please give that a try. It's pretty self-explanatory, going over some of the stuff I just talked about. It has a bunch of examples. And we will just mill around and be here to help you out if you have questions or things. We will reconvene and talk about dynamic features in maybe 15 minutes or so. Is it not collapsed? Oh, it should have been collapsed.
It was called.
Yeah, okay, so you can just press the one. Yeah, we should just. Okay, I can do it.
I would say maybe just go through it a little later.
So I'll pull up the notebook just to make sure everyone's on the same page here with getting it running. So. Um, Okay, so if you go to sceniclang.org, there's the CVPR button up here. And oops. Go down to the schedule here. We've got the two links to the notebooks. We try the first one, for example. So it just has the table of contents and links to other resources, documentation, etc. But you can just go through. The only things you need to get started basically are just running these two cells, and then you can go through all the examples. So this one will install SCENIC. You don't have to expand it and see the details of how we're doing that. But if you run that one and then this one, that will enable you to run these examples down here. So for example, here's like absolute minimum SCENIC program, just says ego equals new object. And when you run it, you'll get this featureless cube at the origin. Okay. And then the tutorial goes from there, building up more interesting scenes. So raise your hand if you have any questions or have trouble, and we're happy to help out. All right, well, I think we'll move on to the second part to talk about dynamic scenic scenarios. So feel free to keep going on that tutorial later. It's hopefully pretty self-explanatory. And if you have any questions, also I'll mention later, we have a new community forum for users and developers of SCENIC, and we'd be happy to answer any questions you have there if you post after the tutorial. So let me switch over then to writing dynamic scenarios. So what we've seen so far in SCENIC can be used to define kind of the initial conditions for a simulation. You can generate just single images, or you could generate a starting point for a simulation and let things go from there. But SCENIC also allows you to describe how agents behave over time in response to their changing environment. So continuing the badly parked car example we had before, maybe we now want to say this car suddenly pulls into the road as the ego car approaches. The way we do that in SCENIC is by giving it what we call a behavior. So here's that little bit of code we had before, basically for creating the parked car. The new bit we're adding here is one last line saying the behavior property is set to this pull into road thing. And that's a behavior that we can define. So the way to think about behaviors is you can think of them as functions that are running in parallel with the simulation. So every agent has one of these behaviors. Every time step of the simulation, each agent's behavior picks which actions it wants to take for that time step. So what this looks like in a diagram is we have SCENIC, we have behaviors for various agents running over inside SCENIC. Every time step, SCENIC gathers up the actions that the agents want to take. These could be things like applying brake or changing the steering, something like that. Sends those over to the simulator that you're using. So for AVs, it could be throttle, steering, turn on your turn signal. These are what we're calling actions. These are basically things you can do in one time step. And they're domain specific. So the driving library that we talked about before defines actions like throttle, steering, etc. If you're working with a robot, you could define actions for, changing the angle of the arm. If it's a robot arm, changing the angle of part of the arm, for example. And the idea of doing this is then we abstract away the details of the simulator interface. So you can write, your scenario in a way that doesn't know about the exact API of whatever simulator you're using. So for example, the driving library we have supports Carla, also this older simulator from LG, SVL, and you could write interfaces to other driving simulators as well. And then behaviors in turn can access the changing state of the simulation to make choices. So we read back from the simulator the state of the world every time step. So the positions and velocities of everything gets updated, and then the behaviors get a chance in the next time step to decide what they want to do. So a behavior looks basically like this. We're saying define a behavior called follow lane behavior. This one takes an argument, like which lane you want to follow. They're basically like functions, so you can have arguments with all that sort of thing. And now we're going to have an infinite loop here where we are computing some throttle and steering to take. Maybe we have some math in here to decide based on the current position, how we want to do throttle and steering. And then we're using the SCENIC take statement to issue the actions that we want. So here it's a pair of actions, this throttle and steering action. So that would be an example of a simple kind of behavior where we're just taking these two actions every time step, and the parameters to those actions, like the numerical throttle and steering, we could compute based on the world state. SCENIC has a bunch of other things you can do to make it easy to write more interesting behaviors. So for example, interrupts allow you to modify an existing behavior without having to actually get in and change its internal code. So here's an example of that. We could define a follow lead car behavior, which starts by doing up this follow lane behavior that we saw before. This is actually one built into SCENIC, follow lane behavior. But during the execution of that, if the distance between us and some other car gets below some threshold, which maybe is a parameter, then we'll switch to some other collision avoidance behavior. And then when that behavior terminates, we will then resume following the lane. That's the semantics of this try interrupt statement. It basically does the try part, monitoring this condition. If the condition ever becomes true, then control goes to this block until this interrupt handler has finished, and then we resume whatever we were doing before. So here we basically added like a special case onto the follow lane behavior without having to actually go in there and modify it. We also saw earlier how you can put requirements on SCENIC programs, like there are some built-in requirements, like objects cannot collide. You can do a similar thing for dynamic simulations. So for example, we could say, I only want simulations where this taxi stays in this same lane for the entire simulation. Or I want at least at one time during the simulation, the ego can see the pedestrian, something like that. And SCENIC will monitor to see if these requirements are satisfied, and if not, it will reject the simulation and try to find a new one. So to give you a more interesting example using some of these features, I'll formalize a scenario from this OAS Voyage dataset, if you've heard of that. The idea here is there's a lead car, which is periodically stopping and starting, and the ego car behind it has to brake to avoid a collision. So we'll start with this follow lead car behavior, which is the same as I showed before. So follow lane until you get too close, at which point go to this collision avoidance, which is basically just going to apply full braking in this example. And here's the more interesting behavior we'll define for the lead car, this stops and starts behavior. So we're going to pick an initial delay between 3 and 6 seconds for when we want to stop. We'll do follow lane behavior until the current time exceeds the last time we stopped by this delay. So here, this simulation is a built-in function which lets you get some attributes of the currently running simulation, and we're asking what's the current time step, and we're keeping track of a variable here of what time step was it when we last stopped. So when that delay has elapsed, then we'll switch to this full braking behavior, and we'll do that for 5 seconds. So this for clause is something you can add on to the do statement, which says run this sub behavior for a limited amount of time. And then once that's finished, we will update the last stop variable saying this was now the new time that we last stopped. This interrupt handler will finish, so we'll go back to doing lane behavior until this condition becomes true again. So what we'll end up with is a car which is stopping and starting, but the time between the stops and starts is the initial one is random, and then we're going to have these 5 seconds. The delay between each of the stops and starts is random. And then we can create the cars using the kind of syntax we saw before. So here I'm just saying the ego car has this follow lead car behavior. The other car will put it 10 meters ahead with this stops and starts behavior. And for this one, just for simplicity, I want to make sure that we're on some straight stretch of the road. So I'm requiring that there's 100 meters of free road ahead of us, basically. So take a point which is 100 meters ahead, and that should still be in the road. Some simple way of requiring that I put in here. Okay. Oh, and we can also put termination conditions. So here I'll say, let's terminate when the ego is no longer in a lane. So if it enters an intersection or something like that, this condition become true. Okay, so here's an example of that scenario then running in the Carla simulator. So you see the lead car up here, it's going to stop, and this one does the braking to avoid that, then time passes, goes ahead, stops again, etc. And the nice thing here is that we could write this simulator, this scenario in a way that doesn't use any Carla specific APIs, and it will just run in Carla. The same one also runs in SVL and other simulators. And here's another instance of the same scenario running. Now we're in a different part of the map, same kind of behaviors being used. Okay, so we also have a notebook for you to play around with these dynamic features. I think maybe just in the interest of time, you can feel free to pull it up. I'll start walking through some of it just so you can get a sense. For this, we can't use Carla because it won't run in the browser, and it's kind of hard to get working on your laptop too. So what we're doing in this notebook is using a very simple Newtonian physics simulator that's built into SCENIC for debugging purposes, basically. So you don't need any extra dependencies to use it. You might notice the physics is not very sophisticated, but it's enough to get an idea of how these work. And then what we can do, if we have time, if anyone has written some interesting scenarios, I've got a remote desktop connection to a server where we have Carla, so I can run some of them in Carla if you want to see what that looks like too. Okay, so I'll just switch over to the notebook then. This one's also linked from the tutorial page. So here's the SCENIC Dynamics tutorial. Starts out the same way as the other one. There's this one cell at the start to just install SCENIC into the notebook. So I've already done that here. So here's a simple example like one of the ones we saw before. So we're going to use the driving model. Here we're using the param statement, which we didn't actually talk about before. This is for setting global parameters of the scenario. So here there's this parameter called map, which the driving model uses to select which map you want to use. So here we're going to use one of the maps from Carla, which is included in the SCENIC repository. And we're just saying create a new car, and its behavior is the follow lane behavior, which is built into this driving model. And if we run that, this is the syntax highlighted version. It's running the simulation, and here for the purposes of the notebook, we've set it up to generate a GIF. So if you run this on your own, on your laptop outside of the notebook, SCENIC has a lot of options for controlling how long do you want to run this simulation and rendering it on your screen. We won't get into that here. This should finish, and then it's also a lot faster, by the way, if it's not running in the notebook. But this is easy to use. So there we go. So here's a road. We've got a car which is being created at some point along it, and it's following the lane. Not very interesting one here. If we ran this again, in the interest of time, I won't do it. It would create the car at some new random point in the road. Okay, so here's just an example where we can make our own behavior. So here we made this kind of silly behavior where we're just taking some constant steering and constant steering to the constant throttle and constant steering to the left. So the car is going to end up going in circles. And this one, we get something like that. So you can see here, this simulator is not simulating, colliding with the curb or anything like that. It just shows a schematic of the road network, and the car you saw started on the road, but because we're doing this silly, I guess it's constant steering to the right, it ends up just going in a circle. So the semantics of these behaviors is basically what I hinted at before. So we have an infinite loop here. So this is going to run for the whole time of the scenario. And what this take statement does is it says, in this current time step, I want to take these two actions. And what SCENIC basically does is it suspends this behavior, sends these actions over to the simulator, simulates one time step of physics, and then returns control to the behavior. So it starts running again. Now this loop will iterate, and then it decides which actions to take in the next time step. Question?
Yeah, the argument for take looks like a tuple of actions.
Right. Yep. So you can give it one action or more in case they're independent. So here, like the throttle and steering actions are independent. So we might want to take those at the same time. You can also do no actions. So we actually have a shorthand for that, this wait statement, if you don't want to do anything. So in this example, I'll start it running while we're looking at it here. It says, while the distance from self, so that's the agent running this behavior, to the ego object is greater than some threshold, we'll just wait. And then once it gets close enough, we'll start following the lane. And then I'm creating a car with the follow lane behavior and two other cars which are visible somewhere from the ego, which have this wait until close behavior. In one of them, I'm using the default distance threshold of 3, and the other one I've specified it should be 6. So it's running the thing. Here we go. It's finished running. So here are those 3 cars. Looks like one of them. So here's the ego. This one, it got close enough for that one to start going. This one, the ego never got close enough for it to start driving in this particular instance. I'll run it again just so we can see if we sample another scenario from the same program, it should look a little different. Okay, so this one, is it going to turn left? Yes. Okay, still too far for one of them, but the other one, it got close enough to trigger it to start driving. So yeah, I didn't mention before, but that follow lane behavior, which is in the driving model, is defined to do something reasonable at an intersection. I think it picks one of the available maneuvers at random. So here it decided to turn left. All right, so we can look at an example of one with an interrupt. Let's see, I'll skip it. You can have if statements and other control flow as usual in Python. Oh, this is one with a pedestrian. So this is one where the car, if it gets too close to the pedestrian, it's computing the distance to the closest pedestrian. If it gets too small, then it will start braking. So here we've got a car, there's the pedestrian. When it gets close enough, it starts braking. Okay, let's do an interesting one with an interrupt. So here we are going to do, I'll look at the highlighted version. We're doing follow lane behavior. When you get within a given distance of any car, then we switch to full braking. So, and then actually looks like I made a sequence of cars with that. So they're all braking. That one didn't brake fast enough.
Did you have to set an exception for collision avoidance?
So here, yeah, so this simulator this simplistic one doesn't model collisions at all.
Okay.
So SCENIC will not create cars at the beginning that are already colliding, but it won't stop them from colliding partway through. I mean, you might want to, in fact, detect simulations where that happened, right? Let's see, how are we doing on time? My notes here. So we want to finish this part around 10:40. Okay, yeah, so we've still got time. Okay. So I mentioned there was that shorthand. Let's look at the highlighted one. Shorthand for running a sub behavior for a given amount of time. That's this for syntax. There's also an until clause. You can run something until a given condition is met. This is something you could use interrupts for, but this is so common that we put this syntactic sugar. So you can say, do the drive behavior until, in this case, the distance from us to the obstacle is less than 10. This other one is just going to drive for 2 seconds and then brake. So if we run this one, here I'm making the ego car starting out. So actually here I'm picking a random road in the whole network and a random lane on that road, creating the ego car on the center line of that, a new car 30 meters along the road from that, and then a final car a further 10 meters from that. So here the ego one is the one in the back. That's here. And it's driving until it gets too close to an obstacle and it stops. The other one is just driving for 2 seconds and then stop. Okay, oh yeah, so this is a little bit of an elaboration on that one that I showed in my slides before, an example where we are keeping some state in the behavior. So this is the driving with stopping and starting kind of behavior, where in this version of that, we're just going to drive until the time since our last stop exceeds some delay. The difference in this one is I'm actually going to pick a new delay randomly. So here the amount of time between the stopping and starting is being chosen randomly each time. Here I'm doing it between 15 and 30 time steps. I think in the notebook we have the time steps set to 0.1 seconds. So this is 1.5 to 3 seconds. And so then we should get this. So it's the ego, it drives, it stops, and it's pausing periodically. Okay, so this is an example of where the behaviors can maintain their own state, so they can make decisions later on based on things that happened in the past, for example. All right, and finally, we have an example using some temporal requirements. So here, I'm going to create a car in the intersection with this drive slow behavior, which is just constantly throttling at a low level. And the interesting thing here is we're going to have a couple of temporal requirements. So we're going to say, first of all, okay, I think actually I might have mixed these up, because we're first saying at some point the ego has to be in an intersection, which is going to be trivially true because we're starting at an intersection. I think I probably wanted this to be eventually it should not be in an intersection, so it should leave the intersection. The more interesting requirement here is using what we call a monitor in SCENIC. So this limit time in intersection, which we defined up here. A monitor is like a behavior. It runs in parallel with the simulation, and it can maintain state and check arbitrary requirements during the course of the simulation. So in this example, it's going to keep track of how much time is being spent inside the intersection. So it starts out setting the steps in intersection to 0, and then forever, it's going to require that that be at most a limit, which in this case is 200. And if the car is in the intersection, then it will increment this counter. And then it will wait for 1 time step. So if we do this, and we get a simulation like this, where it's in the intersection, but it's actually close to the edge of the intersection. So it's not going to spend too much time in the intersection. It's almost out of the intersection. All right, and just to conclude here, this is an example of putting in a termination condition. In addition to putting requirements that you want to enforce over the simulation, you can also say when a simulation should complete, either by putting a time limit or putting some arbitrary conditions. So in this case, I'm saying, let's stop the scenario once the distance from the starting point where we created the car is at least 20 meters. So then here we get a pretty short one where as soon as it's reached 20 meters away, we stop this simulation. All right. So that gives you a taste of this. We have time now for you to fiddle around with these if you'd like. And then I'll mention a few more advanced features of SCENIC at 10:40. All right, folks. So we have just 5 minutes left before the coffee break. So I just want to mention a few other features of SCENIC that we didn't have time to get into, but you might be interested in. Then we'll take a break, and then Eddie will take over after the break, go into more depth about how you actually use SCENIC in some of the applications that Sanjay talked about. So one major set of features in SCENIC that we didn't talk about at all is the ability to compose scenarios together. It's really helpful when defining complicated scenarios to have some building blocks of simpler scenarios which you can then put together. And SCENIC provides various features for doing this, to take scenarios and compose them in parallel, so they run at the same time, or sequentially, so one goes and then when it finishes, another one starts, etc. So there's syntax, for example, where you can import scenarios from other SCENIC libraries and define modular scenarios built out of those. So this is a scenario statement which defines a stop-start with parked car scenario, which is a parallel composition of these two sub-scenarios. One where you've got the stopping and starting car that we had before, and the badly parked car scenarios running at the same time. You can do a parallel composition, so this one would be do the stop and start scenario first. It should have some conditions defined for when it terminates, and then go on to start the badly parked car scenario after that. Or you can do something more complicated using all those features that we saw in behaviors. So for example, here we're saying, do the stop and start scenario until some condition is met, then start the badly parked car scenario. So this is one set of things that's nice for building kind of more complicated scenarios. You could build up a library of common scenarios, then reuse them in this way. I'm not showing it here, but these scenarios can also take parameters like behaviors. So you could say, create 3 instances of the stop and start scenario where the delay in the stopping and starting is different in each of the 3 copies. It's easy to do that. SCENIC also has a number of features for orchestrating running these simulations. So in the notebook that we saw, we had just hard-coded a time limit in there so that you could just see the same one running over and over again. But in practice, you want to do more interesting things than that. For example, recording data from these simulations, not just showing a video, but actually saving some data from them. Eddie will talk more about this later, but the basics are that there's a record statement in SCENIC, which lets you save the value of some expression, arbitrary expression. So here, for example, maybe I want to know a time series of when over the course of the simulation could the ego car, in theory, see the pedestrian versus it being occluded. So here I can say, evaluate the ego can see pedestrian expression at every time step and save it in this time series called PED visible. Maybe I also want to know at the end of the simulation, what was the distance to some goal spot we had. So here I'll just evaluate this distance at the end of the simulation and save that as well. And then when you call SCENIC's top-level API for running a simulation, it will return this data to you at the end. You can also save and replay scenes and simulations. So maybe you're running overnight, large number of simulations. A few of them are interesting. You now want to rerun those and see what happened, maybe look at them in more detail. SCENIC has an API for doing that. So just to give a hint of that here, here I'm calling some SCENIC API to compile this SCENIC program. I am generating a scene from it, and I can serialize that to some bytes. And if I reload those bytes, I get the exact same scene. So everything will be positioned in the same way. You can do the same thing with entire simulations also, as long as your simulator is deterministic. We don't have control over the simulator internally, of course. But if your simulator is deterministic, we can save and restore entire simulations. There's also integration that Sanjit mentioned before with our other tool, Verify, that allows you to not just run independent samples from a fixed distribution that you define with SCENIC, but intelligently try to find corner cases, cases where some spec is violated. Eddie will talk about that in the second half. So I'll just conclude with, if you'd like to learn more about SCENIC, here we just gave a fast overview of the main features. There are lots of resources all available through the main website here. I'll just mention a couple. There's our documentation, which has installation instructions for all major platforms. It runs a lot better if you're not in the notebook. You saw it was pretty slow, but it does work on Windows, Mac, Linux. It's quite easy to install. We've got fuller versions of the tutorials we did today, plus another one on compositional scenarios. There's a syntax guide, which is kind of like the cheat sheets that I showed earlier. It summarizes all of the syntax that SCENIC has, as well as detailed materials on the semantics of all of those. There is a Python API, so you don't have to just run SCENIC like on the command line. If you want to run scenarios in a certain way, collect data, use it somehow, there's an API for controlling SCENIC. And there's also documentation on how to interface SCENIC to your own simulator that you're interested in. Eddie will talk a bit about this later too. And we also have a brand new community forum. Again, it's linked to from the main website. And we have sections there where you can post questions on how to use SCENIC. You have syntax questions, or can I use SCENIC in a particular domain or with a particular simulator? Or I want to get involved in extending SCENIC in some way. How can I do that? All of those things we welcome posts on our forum. All right, so we will stop there. We'll have a coffee break for, I guess, 9 minutes. We'll start again at 10:55 with the last section of the tutorial.
Okay, so we'll go ahead and start the next session on the applications of SCENIC. So now that you understand what SCENIC is about, the purpose of development behind SCENIC, and so the next part is what are the possible potential applications of SCENIC, and the agenda for this session. So we'll break this into 2 parts. The first part will cover about, well, how to do sensor data collection using SCENIC program. And how can we test perception, behavior prediction, and planners with the Verify tool that Sanjay briefly mentioned, and how to interface SCENIC to your simulator of your choice. So regarding sensor data collection, so we've seen you can model a SCENIC program, and you can, and from the SCENIC program, you can sample a scenario generated in the simulator, and you can collect different sensor data with labels and different types of labels depending on the capabilities of your simulator. So for example, semantic segmentation, LiDAR, and so on, as you can see. So how can we do that? What I'm about to show you is a way to do that in the SCENIC program. So first of all, I'll skip over, just if you could focus on the part in the pink box. For example, with ego, once you model the ego as a new car at a certain spot and so on, you can now add this with sensors part. And here, assuming that you already modeled what sensors are in a different file, you can call that sensor and say, hey, I want the RGB sensor, and the offset over here is the offset with respect to the center of the vehicle. So I wanted 1.6 meters forward at the center, and a Z offset 1.7 meters up. You can place the sensors at the location that you want on the vehicle. And likewise, for example, in this case, semantic segmentation sensor, which is providing the label in this case. So you can specify which sensor you want and where you want to place the sensor at. And then at the below, you see a record statement, which says, okay, so once you specify the sensors here, those are already automatically now specified within the observations properties of ego as the same name, using the same naming convention, which is the front RGB and front SS, as you can see. And then here, I'm just redefining that as front RGB. So after you run SCENIC, you get a simulation results object within which you can search for the data that you asked to collect over here, which I'll show you later. And what's nice here is that you can also specify at what polling rate that you want to collect the sensor data for. So in this case, you say, hey, for the front RGB camera sensor data, I want to collect at every 0.1 second. Likewise for the semantic segmentation label as well, right? So now to motivate why we may need Verify. So right now I just gave you a introduction as to how you may collect data using SCENIC program. Now the question is, isn't that enough to test your potentially perception, behavior prediction, and planners? Well, there are some challenges to think about. So for example, as you saw, SCENIC is not just modeling a concrete scenario, but a distribution of scenario. So the question is, well, how are you going to search through this distribution? Right? Potentially, you can sample infinitely many scenarios if there are especially distributions over continuous variables. And there may be 2 different objectives. One is to explore, sample as diverse environments as possible, variations of environment possible, as specified in the SCENIC program. But at the same time, you also want to exploit, as in you want to find as many counterexamples as possible that violates certain specifications of your system. So how do you balance those two things as you're sampling and to sample and generate data in order to test your machine learning models? So that's where Verify comes in. And as Sanjay briefly covered, Verify is a supporting toolkit that we developed around SCENIC. And Verify takes in the model of the system, model of the environment, which is in the form of SCENIC program, and your specification over these, your machine learning models. And given that, from the SCENIC program, it extracts out, okay, what is the distribution space that are modeled in the SCENIC program? And then specifically, the search part is what's nice about Verify. It supports different sampling strategies that trades off the and balances the trade-off between the exploitation and the exploration constraints that you may be interested in. And we support Bayesian optimization, multi-arm bandit, cross-entropy, simulated annealing, and so on. And you can also add your own samplers as well. And what's happening here is that given that distribution space, we sample, and also given this specification here, we sample an environment, sample a scenario generated in the simulator, and then compute whether the specification has been violated in that scenario. And then we log that information, and that information gets feedback to the sampler. And so that the sampler, the search engine that we have, is now getting a history of how the system has been performing in the different environments that has been sampled. Yeah. And it's supporting various use cases as you see on the right side. Cool. So now, how can we test your ML models, like perception, behavior prediction, or planners, with SCENIC and Verify? So first of all, from SCENIC side, as we mentioned, SCENIC is embedded in Python, so you can actually import different Python packages like that. So you can import, for example, PyTorch, and then load your ML model at the top in the pink box. And at the below in the pink box, you can call your ML model and then feed in the sensor information that you're collecting, for example, front RGB camera, along with its label, which in this case is semantic segmentation, and then save it at certain polling rate that you may want, right? And then on the Verify side, here's a part I'm just giving you a snippet where you now specify your specification here. So we give you, all these are well documented on our website, and I'm just going to show you a brief snippet, the main parts. So in this case, we provide you the template as to how to write your own evaluation metric. And in this specification function, which you have to fill out, it already comes with an input argument called simulation results. And then in that simulation results, previously we were saving the ML performance results at every 0.1 second. Now we're accessing that information, which is a time series data. And then let's say you're computing your mean intersection over union. You can write your own Python function, evaluation metric defining that, and then return that. Yeah, and then in terms of, in Verify, you can also specify, so that's how you model your evaluation metric. It's quite flexible. And in terms of running the Verify, you can actually specify different aspects. So for example, here, these are the parameters that you can control. One is how many simulations do you want to run? In this case, let's say I want to run 1,000 simulations. And then for each simulation, what is the maximum amount of time you want to run each simulation for? You can say, in this case, I was setting it to, let's say, 20 seconds. And then is there any threshold that we want to impose on the evaluation results? Let's say in this case, it's a mean IOU. You can do that as well. And then this falsification threshold is determining what is correct, whether putting a threshold on the correct or incorrect. So if it's, let's say, above 0.5, then the system is performing correctly, below, not. And then also it asks, as I mentioned, verify is collecting and logging the environments that SCENIC is sampling, and also logging the system's performance there. So in that case, do we want to save instances, save the environments which led to the failure of this system that you're testing? If you want to do that, then you can set this to be true, and this will save a CSV file with all those information, which I'll just show you in the next slide, as well as the save table, the environments in which your ML model is performing safely, and so on. There are other parameters as well, but those are all well documented. So here's a quick demo video. So for example, you're running the SCENIC program along with verify, and let's say it was a badly parked car case that Daniel was showing you before. We may be running this. In this case, I set it to 3 times. So it would run 3 different instantiations of badly parked car cases, and then generate the safe and the error table accordingly. What you'll see soon is that in this case, we couldn't find any, because we were only running 3 cases, 3 scenarios, we couldn't find any cases where it led to violations. So in this case, it was only saving safe table. And then if I quickly fast forward, I can import this into, open up this CSV file, and then in a Google Sheet, and see what kind of environments has been sampled. Like for example, what was a RGB color, what was a car model of the other agent, what was its position, and then what was a corresponding ML performance results in those sampled scenarios. Yeah. Okay. Any questions so far? Yes.
In the previous diagram, you showed that there was a component that is called searching.
Yes.
It's used in the really long rectangle. How many people go?
Right. So if I may go back, it's it can be used for different purposes. One big use case is what we call falsification, which is to search for, and search here means sampling, right? Sampling from the distribution of scenarios that's modeled in the SCENIC program. And the purpose of sampling is to search for scenarios which leads to the violation of this specification that you're providing. Yeah. Okay. Yes.
That search is just random, and it actually tries to sort of home in on the places where things are going wrong.
Exactly. Yeah. So there are different use cases, but in your case, as I mentioned, this monitor is feeding in and providing a history of the sample environments and how the ML is performing, and that history is providing some intuition to a different sampling mechanism as to how to intelligently sample the next one. Yeah.
Yeah, just to add to that, I think to think of search techniques as being of 2 kinds. One which is active, goal-directed based on the specifications you provide, and the other which are passive, like random sampling or Hawkins sampling. There's really that's a partial list. You can add your own approach to it.
Yeah. Any other question? Okay. No, I'll move on. All right. So the final part is interfacing SCENIC to your simulator of choice. So how can we do that? I think Daniel mentioned as to how SCENIC and the simulator interacts with each other at every simulation time step. So for each interface, we need to create a simulator.py, which we provide a template for. And then within each template, we provide annotations as to what you need to fill it out for, what is the purpose of the function, which I'll show you in the next slide. But the role of that interface is to, first of all, initiate that client-server communication between SCENIC and your simulator of choice, and then basically be able to instantiate and create objects in the simulator through that communication protocol, and then control the actions of each agent, and then simulate the actions for one time so that and update the state of the world and so on. So let me give you some example. So for example, at the beginning, you need to create this initial client-server relation. So in the template simulate in the templates simulator.py code that we provide, in this init function, that's where you may want to create the client-server communication between SCENIC and your simulator using the APIs that are provided in the simulator, right? So that your simulator may provide API to, I mean, it must be providing some mechanism for you to control the agents in the simulation. So what is that API? And then let's use that API. In order to use those APIs, first of all, we need to create this client-server simulation. The second part is, okay, so once we created that, instantiated that as client-server relation, now SCENIC program gets executed, samples a initial state, initial environment, and then sends over to samples that initial environment. And now we want to instantiate that initial scene in the simulation. So this create object in simulator is the function that is doing that. And now here within this function, you want to use the APIs of your simulator to enable that, right? And this object input argument that you're seeing is information about each object that are sampled in the SCENIC program and its properties. Like what are its positions, orientation, car model, whatever. Yeah. Okay. And then the step function is what is executing. So the action or instantiation of the object in your simulation for one time step. So basically, it's executing one simulation time step in your simulator, and running, updating the state of the world in your simulation. Yes.
This is for your logic nodes for the agent that is driving, for example.
Logic as in, so SCENIC at every time step is sampling based on the state of the world in your simulator, is sampling what action to take for each agent in your SCENIC program, right?
Right, but for example, so let's say you have some machine learning model, and is this a part of the simulation or is it something else?
Yeah, sure.
So if I understand correctly, you're saying, like, if I wanted to have define an agent that uses some ML model to make some decision,
Yes.
would that be called from this function?
Yes.
So this function is actually independent of which scenario you're trying to run. This is a function you only write once when you're interfacing SCENIC to the simulator. This just says when SCENIC wants to advance time, what simulator-specific APIs does it need to call? If you want your agent to invoke an ML model, that would be in the behavior you define for the agent, which will be in like the fascinating.
Okay, thank you.
And then the next part is, well, how do you update from the SCENIC side, its understanding of the world state at each time step? So this is the function that you need to update, which is get properties. And this is the part where you use, again, your simulator's API to, get the world state information as to what are the properties like positions, orientation, speed, and so on of each objects in the SCENIC program in your simulator. And then execute actions is the part where now, once you got that state, updated state, SCENIC will internally update what action to take for each agent. And this is basically compiling all those actions per object to simulate. And then by executing the step function again, that is now executing all those actions for one simulation time step in your simulator. Yeah. So that's it. I can go into much detail, but due to limited time, I'll refer you to the SCENIC documentation regarding this matter. But that is sort of the highlights of the details that you may have to consider when interfacing SCENIC to SCENIC. Yeah.
The examples you've shown have been, I think, simulators that are sort of serial, running one simulation at a time. Could SCENIC support simulators that are from parallel simulations to sort of sample lots of things in parallel?
Yeah, actually, we did work on that before, and it was published to a conference. So long story short, yes. Yeah.
We can give you more details.
Any other question? Okay. So in summary, we covered flexible sensor data generation using SCENIC. Oh, one thing that I want to mention is that this capability for number 1 that I mentioned is not pushed to our repo yet, but it's coming very soon. And Daniel pretty much implemented the whole thing. We're in a testing phase just to catch any bugs. Yeah. We also covered how to test perception, like different ML components using SCENIC and Verify, and also covered that SCENIC is not specific to any simulators. You can actually interface to different simulator of your choice. Yes.
The coverage of
Yes. So the question was about how do you reason about what was the coverage space of the after sampling and testing in different scenarios from the SCENIC program, how do you reason about what was covered or not? And as Sanjay was covering in some of his examples using the flight simulation and so on, it was showing you the plots, right? And how is he showing the plots? Basically, I mentioned in Verify, it's logging all the environments that it sampled and the performance of your ML components, right? So using that information, you can plot those kind of and visualize those plots in order to visually also reason about the coverage as well. But also in Verify, we provide like different k-means clustering algorithms and so on to reason about those aspects on the log information.
The other coverage metric of choice is very easy to implement that on top of the infrastructure that I use, right?
Yeah, and as I mentioned in Verify, you don't have to use our samplers. You can add your own samplers with your own coverage notion. Anything else? Yes.
So maybe just from experience, could you tell us a little bit about what was the scale of the size of the problems that you have been successfully working with? So for example, are we talking about 100 variables, 10,000 variables, and how the search space works in those conditions?
You want to go?
So one thing which I think we mentioned a little bit before, but we didn't stress that much, is that SCENIC and Verify are operating on what we call a semantic feature space. So like high-level parameters like the position of an object, the orientation, that sort of thing. So most of the problems we've looked at, the dimensionality of the space is actually relatively low because we're taking that kind of high-level description. We're not working on pixel-level images, for example, right? So I think we've done some where we've had, say, a dozen or a couple dozen semantic parameters because we had several objects or maybe up to a dozen objects, each of which has several parameters, position, orientation, and so forth. But even in like fairly complicated driving scenarios that we looked at, like, I don't know, bumper-to-bumper traffic with a dozen cars or something like that, the actual search space did not get too huge because we're taking this high-level view of semantic features. If we looked at the actual raw features going into, say, the perception model, of course, the space would be huge there, but we're not searching directly over them. We're searching over these high-level features, which we then use, which we then turn into actual data using SCENIC.
Right, but then the boundary is somewhere, fuzzy, right? Because then you can, obviously you can model semantics of the world itself, but then you start considering things like weather, environment,
Right.
And maybe some perception components. So for example, how do I find that my person detector fails for women in red dresses, for example?
Right. So yeah, you can add parameters saying, for this pedestrian, what's the color? Like the color interface allows you to change the color of clothes, for example. So you would have parameters for that. There are also several different pedestrian models, et cetera. So you could parameterize over those. So yeah, I mean, we've done scenarios with, say, a few dozen such parameters, and it seems to work okay. But yeah, it really depends. I think the scalability is more a function of the structure of the type of scenario you're trying to find. I think the hard part is finding the corner case. Even on a relatively low-dimensional problem, it can still be difficult to find.
Yeah.
Also, length of simulation. I think for us, what in our experiments, it's not really the dimensionality of the SCENIC program, but just running really long simulations. That becomes the performance bottleneck. And so there, SCENIC's compositional semantics helps. If you can define a very complex scenario as composition, parallel, sequential, random composition of these smaller ones. We have some recent work which exploits that. So we can have a great conversation about around the forum.
Yeah. Just to add to that, I think the parameter space can start to get more and more depending also on the number of agents and so on. And if you're simulating at a traffic level, that can be a lot. But I don't think we've tried at that level. Yes.
You may have said this and I missed it. If you find a corner case, do you have a way of generating new cases that are near that corner case to, sort of speed up the scenario?
Yeah, exactly. And when I was covering the verify part, I was mentioning about, well, why do we need verify? You may need to trade off the balance between the exploration over here and the exploitation, and I think you're talking about exploitation is how do we find more and more variations of the counterexample that you found. But at the same time, you also want to diversify, right? So that's why we're coming up with verify to provide some of the algorithms, samplers that trace off those balance, and you can tune how much of the balancing you want.
Kind of like genetic programming. You want to
that could be one of the search engines too.
champions, but have some diversity.
So second part is I'm going to cover 4 different cases. So one is, well, once we test and identify failures, how do we debug the machine learning models? And the second part is, how do we do sim to real validation? And third part is a sensor data exploration, which is in this era of AI, when industry and academia are collecting so much terabytes of data and labeling them, it's not just about the size of data, but also contents. So how can we query through the data, and then retrieve sensor data set that matches the scenario description that's described by the SCENIC program? And then the last part is about extended reality. So first is debugging machine learning models. So this was published at CVPR. And given a user's scenario, with nominal distributions, what we do is we generate, in this case, for example, like 1,000 different images, or many number of images through a simulator, which in this case we were using GTA 5. And then we want to infer certain rules, semantic rules that leads to failure of the system that you're testing, which in this case was a neural network-based object detectors. Likewise for success inducing. And once you extract those rules, we can add those rules back to the original scenario that was given as an input to refine the distribution space of the SCENIC program, and try to generate more of the data and see if that actually induces more failures from your system or success from your system. And in this way, you get an explainable interpretation at a semantic level of what semantic features are affecting your machine learning model's performance, as well as you can also systematically generate those sensor data that are inducing certain behaviors from your system or models. So, so how that works, just to provide background, is that SCENIC, at each execution, in this case, we're only looking at static scenes. And in this case, at each execution, SCENIC is generating scene, and that gets fed into a simulator, and then it creates, and the simulator renders an image, and then we feed into the neural network perception model, and then try to determine whether it was performing well or not. And how does that scene look like? As you saw, it's like over weather condition, car model, and so on. And then we're also logging information about how your perception model is performing on those scenes that we sampled. So this is a classification problem now, right? So that's how we formulated the problem. And then just jumping to the experiment section, we, for example, tested this in 4 different scenarios. I'll just cover one. And the scenarios are on the left side, and the rules that we inferred that are failure inducing are on the right side. And this percentage over here is before and after we refine the distribution space by adding this semantic rules. And so, for example, when we generated 1,000 images using the SCENIC program that was nominally given, the perception model was, let's say, failing about 35% of the time. But after adding these failure-inducing rules, it bumps up to close to 90%. Right? And let me share you one interesting case that I saw that what I thought was counterintuitive, is that here in this case, I was expecting that perception model would fail if the car is further and further away. But actually, no. Counterintuitively, we see that if the car of a certain model, which in this case is Pranger in GTA 5, is within certain distance, in this case 8 meters, then the perception model tends to fail more and more. And we see that on the right side. We generated and also confirmed that as well. So this is how we are symbolically searching for semantic rules that can explain, and we can also validate using SCENIC. I'll skip this part. And then the second part is sim to real validation, which Sanjit also covered, which is well, we're using simulation right now and testing these systems using synthetic data. Well, how do we know whether these failures actually occur in reality or they're occurring because of some spurious artifact of the synthetic data that may not actually occur in real sensors, right? So there can be many potential causes. For example, differences between synthetic and real data, dynamics model, agent behaviors, and so on, which is why we worked on this example that Sanjay showed you before and worked on carefully selecting test cases that we want to reconstruct and replicate at a track testing site. And the experiment result is that regarding the unsafe test, so meaning failures in simulation, which led to severe violation of the specification that we had, was about 62.5%. Regarding test cases which was marginally safe, so it was violating but not to a severe extent, was about 90%, and robustly safe, meaning this behaviors, test cases that did not violate the specification, was 100%. Yeah. Now the next part is, again, sensor data exploration. Okay, so going back to the narrative, there are tons of data that are being collected. And the question now, and I think moving forward, is it's not just the size of the data, but also the contents of data. And what I mean by that is, for example, if you have a self-driving car training data set, and it does not contain any unprotected left turn scenario, well, that's an issue. So how can we actually help and algorithmically help researchers and developers explore and understand the data set? So in this case, what we do is, given a SCENIC program, let's say that you identified in simulation that is modeling a distribution of failure scenarios. But that's for now what you found in simulation. And given a labeled real-world data set, we want to identify the matching subset of that real-world data set. And how do we do that is the problem that we were looking into. And here we're using SCENIC as a query language to model, first of all, the scenarios that you want to look for, and then output and retrieve the sensor data that are matching that description. So in particular, we're not looking at the level of sensors, high-dimensional sensors, but we're looking at the labels. And the question is the label in the support of the distribution of labels that SCENIC program is defining? And again, we're particularly looking into the static case as of now. We're currently extending this to enable video query, but at this point we're querying, you can think of it as images. And these labels contain information, semantic information, such as what is the time of day, positions and headings, which in the case of real data set can be retrieved through localization techniques like SLAM. So the methodology is quite straightforward, which is to convert the SCENIC program into mathematical representation, which in this case is SMT formula. You don't have to know what that is. And then we use a solver and then compare the label to see, okay, are the information in the label satisfying the constraints that are specified in the SCENIC program? So we conducted an experiment with human participants to address following hypothesis. One is, yes, we can query for interesting and realistic scenarios. And the second part is that the output of the algorithm matches the intuitive notion of scenario matching of humans. So we recruited 3 participants, gave them 5 different scenarios with, in this case, new scenes, RGB images, and then asked them to retrieve manually these matching images. And then we took an intersection of each subset to find the most accurate, given that humans can have some human errors. And our experiment shows that, first of all, in scenario, I'm not going to go over what each scenario is, but in scenario 5, there was supposed to be no scenes matching. That was the case. Oh, so just to explain, the first part is images that humans found. The second part is the images that our algorithm found. And then regarding the scenario 3, this was a potentially hazardous case where the car with the camera is going over the yellow line in order to bypass a car in front. And some of our participants completely missed retrieving this, whereas our algorithm was able to. And in this case, we were able to find all 5 scenes that the humans manually retrieved, but also found 2 additional ones that humans also missed, which in this case is that on intersection, find all the scenes where 2 cars are going in an opposite directions. And in this case, there's a barely, you can barely see what's happening because of the occlusion. But so humans missed that, but our algorithm was able to retrieve. This also has some limitations though, which is that in this case for scenario 1, our algorithm was finding 16 more cases than what participants were able to retrieve. But the reason, but those had some errors. The errors attributed to the errors in the labels. So that is a limitation. And the last part is extended reality. I'll just go through this briefly. Using SCENIC and Verify, basically, we're modeling a different library of SCENIC programs, each program associated with each motor skill that we want to train for humans. And in this case, we're modeling the prerequisite relations between each motor skills. So A, B, and C, each node over here relates to each motor skill that we want to train people for, and each skill is associated with its own probabilistic program, SCENIC, and its evaluation metric. Then given that, we were sampling from that SCENIC program and generate that scenario or task in VR, and then collect the user's trajectories and actions to evaluate the task, and then evaluate the user performance results, and so on. And then regarding this part on the right side, it's basically it's inferring its belief state of whether the human has actually acquired the skill or not. I wouldn't go too much into that detail. And so, for example, just to show the kind of environments that we're generating, for example, we're varying the speed and orientations of the teammate that was teammate player that is flying around, and then given that human was supposed to accurately pass the frisbee disc. Oh, this is it's called Echo Arena, which is a game from Meta, and it's basically zero gravity frisbee game. So you fly around and then play frisbee in that sense. So quick experiment results, just to show you is that basically we were able to train people to acquire skills. And in this case, we were comparing between the control group and the experimental group. Experimental group is being trained with our algorithm, which is using SCENIC and so on to personalize the curriculum and so on. And the control group is using self-guided learning, where one is predicting on one's own skill acquisition and creating one's own curriculum that way. Yeah. So with that said, we covered different applications of SCENIC, testing and debugging machine learning models, test case generations for track testing for sim-to-real validation, and sensor data exploration using SCENIC as a query language, and training humans for motor skills in extended reality. Yeah, with that said, if you have any feedback, we'll appreciate it.
I think videos put us back on track. So, any questions on this segment?
Yeah.
Could be to generate environment for things like reinforcement learning, what kind of thing?
Yeah. Yes. Oh, maybe I should have covered that too. Yeah. So as Sanjay covered in one of his examples, we interface SCENIC to Google Research Football Simulator, which is meant for training reinforcement learning agents, and we publish their results to AAAI. And yeah.
All right, so we are close to the end of the tutorial. And so I'm just going to do a quick summary of what was covered here. And we'd love to get feedback. So we started out talking about the context, the verified AI agenda, and introduction to our open source tools, SCENIC and Verify. And I talked about these two industrial case studies we did, one in the avionics domain in collaboration with Boeing, the other one in the self-driving car domain in collaboration with AAA and LG. Then Daniel led the hands-on introduction to the SCENIC 3.0 language. And for those of you who haven't tried out, the website has the links to the two Google Colab hands-on tutorial examples. So please go through that if you haven't had a chance to do that. And then we talked about a bunch of applications of SCENIC, synthetic data generation, testing and falsification, interfacing to simulators. We talked about debugging ML models, especially in the context of perception, to try to understand what the failures are and why. We talked a little bit about using SCENIC for sim-to-real validation, part of which is querying label data with SCENIC, and then an application that's training people to perform tasks in extended reality. So I also wanted to summarize the different features that we covered. This might be, it's a long list, may not be fully exhaustive here. So, all of these bullet points are different features of the language that were covered, right? So you've got object-oriented features, you can model spatial constraints, 3D geometry, and put distributions and everything. Local coordinate systems, so you can specify positions relative to of one object relative to another one. You have the notion of specifiers, you can add declarative constraints. You can have externally controllable parameters. I think Daniel mentioned this, but maybe we didn't highlight it enough. So one aspect of SCENIC, of course, is you can model the world with all these variables and you can put distributions on them. But you might also want to have certain variables, we call them parameters, that are adversarially controlled. So you don't necessarily want to assume that you have known distributions over them, and you want your external falsification or testing or verification engine to be controlling the values of those things. So you can do that in SCENIC. You can define parameters and you can control them through your favorite verification search algorithm or testing algorithm through Verify. He talked about dynamic aspects of SCENIC. You can model agents and their actions and behaviors. You have interrupts, termination, and so forth. We have the notion of a monitor. You have constructs for logging simulation data and collecting sensor data, as was covered. And then the other piece of SCENIC, which I think really helps in the scaling up aspect, as was asked about, is composition. So for anything to scale up, you really need to make the underlying techniques modular and compositional. And so in SCENIC, you can build up complex scenarios from simpler ones, and you can use that structure in the underlying algorithms for testing and verification and data generation and all of that. So we covered a whole bunch of use cases, but there are certain ones that we did not talk about. So we have in Verify, we have a number of methods to specify requirements. I talked a little bit about using logic. That's one way to do it, but it's not the only way. You can also write requirements as metrics with objective functions, so reward functions, cost functions. You can specify those as well. And then you can also write your own monitor as custom Python code that simply takes in a trajectory and evaluates some metric or property over it. And the other thing you can do is you can add all of those together in a more complex structure and create a multi-objective specification, because a lot of autonomous or robotic systems don't have just one property or metric they want to satisfy. There are multiple things, and often there are priorities between all of these things. So we have an experimental feature right now that should be, I think, released in the next year, where you can create what's called a rule book, which is a multi-objective specification. We can do falsification, as we talked about, but we can also do what is called statistical model checking, which is a formal verification technique that you can use to get stronger guarantees using simulation. Do debugging and triage, data augmentation. These are things we talked about earlier. We can do goal-directed parameter synthesis. So this is an idea where you can say, I want to train my model, or I want to synthesize values of certain parameters in my controller so that a certain specification is satisfied. So we have some capabilities there. We can do runtime monitor generation, which is something that I alluded to, but we didn't really talk about the how. Sim-to-real validation, training RL agents, as was asked about recently, in the previous session, and training people in extended reality. And I think these are all applications that we have developed often in collaboration with others. And so really one of the things that we'd love to do is collaborate with all of you in the room on developing even other newer applications of SCENIC. So if you think of if you have a new use case that you've thought of and it's not on this list, or maybe you think it's not well supported, let us know. And we'd love to work with you on that. Okay, very quickly, I want to mention a couple of things before we close. So there was a question earlier from one of the people in the audience about, well, how do you know that you've generated a SCENIC program with all the variables you need to model? Okay, and of course, when we started out SCENIC, we were writing examples by hand, and of course, you think about it and you model the world, and our users did the same. But over the last couple of years, with large language models generating code, we've looked into also generating SCENIC programs, and we've had some success with that. Very preliminary work, but looking a little promising. And so the idea here is to generate SCENIC programs from natural language, right? Just like other text-to-code projects. In particular, we've built a system called SCENIC NL, which takes this input, sort of more or less, it's been tested mainly in the autonomous driving domain. So it will take an input, something like a crash report or an incident report. And in fact, we have applied this to over 500 reports that we scraped off the California DMV website. And it goes through a pipeline, and at the output, we generate a SCENIC program that models that. And this is a collaborative project with many people, including myself from Nissan in the room here. So I want to just give you an example of one of the things that we did with this. So this is work that is led by my PhD student, Kareem. So the scenario description is up there. So I'll just read it out to you. It says that a Cruise autonomous vehicle operating in autonomous mode was traveling eastbound on Clay Street at the intersection with Kearney Street. When it slowed down, the driver of the Cruise AV disengaged from autonomous mode, and shortly thereafter, a bicyclist proceeding straight made contact with the right rear fender, damaging its fender. The bicyclist left the scene without exchanging information. There were no injuries, police were not called. Okay, so that's the description. From that, the SCENIC NL pipeline generates the code that you have here on the left. Don't expect you to read that, but you'll see there's there's an ego car, there's a bicycle car, it has behaviors, they're defined up here. On the right, you see a rendering of that in Carla, and let me move this away so you can see the rest of it. And so what we see here is, it seems at a very high level, it's doing something that matches the scenario, but not perfectly, right? So the bicyclist does hit the fender. It's not the right rear fender necessarily. It's somewhere in the middle, and then the bicyclist leaves the scene. It's not necessarily at the intersections, etc. So there's more work to be done here. But we've got an initial pipeline where at least I think it does a reasonable job of the initial spatial configurations and what objects are there and so on. And then you can, the way we think of it currently is it's a way of starting out with something that a person can then go in and modify. Although there's ideas to apply other kinds of program synthesis technology here. All right, so with that, I would like to conclude. I want to remind you that we have this website, sceniclang.org, CDPR24. So the slides are on there, and the Google Colab notebooks are also linked from that. And as Daniel was saying, we have detailed documentation, and importantly, we have a community forum. And so if you'd like to, if you use SCENIC or you'd like to contribute back, or you have questions and you have feature requests or other ideas, please join our forum, and that's the best way for us to communicate. I want to advertise that we have a more in-depth workshop coming. So end of August, we'll have a 2 to 2.5 day workshop / boot camp, where we want to essentially have people who would like to learn to become kind of power users of SCENIC and also contribute back to the project. We'll have a workshop at UC Santa Cruz. So if you're interested in this, let us know. We are thinking of making this a hybrid workshop. So people who can't make it to Santa Cruz, although I'm sure many of you would love to, and we'd love to have you there. It's a good time of the year to be there. We'll have a Zoom option, I think, right? So anyway, so let us know if you'd like to be there and participate in the workshop. All right. And with that, let me put back the link as well as the QR code for our feedback form. So if you could take a few minutes to fill out that form, it'll be super helpful to us. It's a very short form with a text box at the end. So please let us know what you thought of the tutorial, what you'd like to learn more about, if you have any ideas about the SCENIC project, new use cases, feature requests, all of that. Feel free to put that in there. Okay. Anything else, Daniel, Eddie, Armando? Okay. Thank you all very much, and we'll be around here at CDPR today, and we'd love to have longer conversations with you all.